Alright, we're going to do 15, which I know is the one that we didn't get to spend as much time on in class. This will be a little bit of work here to talk through. Um, and I should also add in that it depends on where you round things as to what answers you will get. Everyone should end up with the same answer for Rachel, but Keenan is kind of right on the line, so as we'll see working through this, depending on where you round things can depend on what you end up with for him. So as long as your work matches up with the answer you get, that's fine. First thing to understand with 15, what it tells us is two students in different classes took a test. Okay, so it goes on to give us that Keenan scored an 85 on his exam. His class had a mean of 75, standard deviation of 6. Rachel scored an 85 on her test, but her class had a mean of 75, standard deviation of 4. Anytime you are given two complete sets of data, meaning you have a data value, you have a mean, you've got a standard deviation, you have two full sets of that, pretty good clue that you're probably going to be working with z-scores, because a z-score requires all of that data, and so if you have two full sets of that, what else are you going to do with all that data, with all that information? The important thing with this is the question asks which student, if any, scored in the top 5% of their class. It does not say which student did better. It's just asking who scored in the top 5%, meaning you should really look at these as two separate questions because it's possible neither of them scored in the top 5. It's possible both of them did. They're really separate from each other. Okay? So let's start with Rachel just because I think she's going to be the easiest one to deal with this. Also, you will need your z-score chart for this. If you don't have it with you, you can just look it up online. That's what I'm going to be doing is I've got my laptop in front of me, so I just have pulled up the z-score chart on Google Images, and that's what I'm going to use to work through this. But you will need that. So with Rachel, let's calculate a z-score for Rachel. So z-score, remember, is your data value minus the mean divided by standard deviation. Data value minus your mean divided by standard deviation. Rachel's score was an 85. Her class average was a 75 with a standard deviation, it says, of 4. That would be your setup then for finding z-score. Data value meaning the score that Rachel herself got, the part that would change person to person, minus the mean, which should be the same for person to person, divided by the standard deviation. So 85 minus 75 is 10. Then you're going to take 10 divided by 4. Your z-score chart goes out to 2 decimal points, to the hundredths decimal point. So my recommendation would be if you have 2 decimal points or more, you should keep those 2 decimal points. Now in this case, it doesn't really matter because 10 divided by 4 just gives you 2.5. Right? So it doesn't really matter because you don't have anything to round because it's just an actual answer. So we would go to our z-score chart, or I guess I should maybe even just show with a picture. Remember what this means. 2.5 is a measurement of standard deviations. So it's saying if you think of this as a generic normal distributed curve, here's your mean, here's 1 standard deviation, here's 2 standard deviations, here's 3 standard deviations. Rachel's score is right in the middle between the second and third standard deviation. Now, if you think about this, we don't even need the z-score chart for her because 68% of the data is covered within 1 standard deviation. 95% of the data is covered between the first and second, between the second standard deviations, both to the left and to the right. Okay? If 95% of the data is covered within 2 standard deviations, and Rachel's already passed the second standard deviation, she's clearly in the top 5% because we're already talking 95%, and 100 is the highest you can go. So I guess maybe I should have said that before. When it asks if a student is in the top 5% of their class, that means they're higher than 95%, right? Because if you're in the top 5%, that means you scored better than 95% of your class. So Rachel being outside 2 standard deviations guarantees that she's got to be in there. Because let's remember, when we say that 95% of the data is housed within 2 standard deviations, that's more than 95% for her, because there's 5% left, and 2.5% of that is over here, 2.5% of that is over here. So she's even above the 97%. She's even higher than 3%. She's in the top 2.5% for sure. Now, let's talk about Keenan because he's not quite as guaranteed. So we need to calculate a separate z-score for Keenan because he's in a different class, different information, okay? Now it does say that Keenan still scored an 85 on his test, so that's still our data value for him as well. His class also had a mean of 75, so that part stays the same. Really the only difference is the fact that his standard deviation is 6. 85 minus 75 is still 10. Surprise, surprise. So now we're just taking 10 divided by 6. This is the one where you choose to round matters. 10 divided by 6 is 1.6 repeating. If it's 1.6 repeating, that means really you should be treating this as 1.67, because 1.6 repeating means you just got a bunch of 6s, right? And so 6 would round up, so you would count it as 1.67. If you kept this as just 1.6, you're going to get a different answer off the z-score chart, and you may end up with him not being part of the top 5%. We're going to work with 1.67. If you did it with 1.6, it's up to you if you want to go back and rework it, or just remember to round to 2 decimal points on the test. That's not a big deal, okay? If you go to your z-score chart and you look at 1.67, looks like you would get 0.4525. If you look at your z-score chart for 1.67, looks like you should get 0.4525. Okay? If that's the case, that means that they are telling you this is 45.25%. What you have to remember, though, is what the z-score chart is really showing you. If this is your normal distribution, which is not even, so we're going to erase off a little bit of this to make it even. Looks better. Here's your mean. If Keenan scored a 1.67 for his z-score, here's 1 standard deviation, here's 2 standard deviations, he's somewhere around here. That 45.25% is from the mean to this dot. That is 45.25%. What it's not including is all of this 50% over here. Think about this in real life terms. The mean was 75 according to this class. If the mean is 75, that's right here. There's tons of other scores over here that you could get, right? Somebody's failing this, somebody's getting just a 72, somebody's getting a 68, D+. There's plenty of scores back here. Keenan's getting a better score than all of those people because he got an 85. If they got lower than a 75, he's got a better score than them. So it's not just 45.25%. We have to add 50% to that. That means he actually scored better than 95.25% of his class if you used the rounded 1.67 as opposed to just 1.6. So technically, if he scored better than 95.25%, that means he's in the top 4.75% of his class, so Keenan is actually in the top 5% of his class, meaning the correct answer, if you rounded to a hundredths decimal for each of these, would be, yes, they are both in the top 5% of their class. Rachel certainly did better than Keenan, As far as her classmates are concerned, she definitely did better than more of her classmates than Keenan did, but they were both in the top 5% of their class, just barely.